Hello, welcome to the recitation week 7 for EE2423 network theory. Today's topic is about first order circuit. So we have a circuit comprising of resistors, current source, voltage source, as well as inductors and capacitors. So the basic here is you have to know the equations expressing the voltage and also the currents of inductors and capacitor. Okay, so as a review, so you have inductor, so this is inductor. So inductors and capacitors, they have the ability to store energy. So this is, say we have inductors, the inductance is in Henry, so L is the inductance, the unit is Henry, is the voltage VL, and the current going in to the inductor is IL. So we know that the current flowing through inductor, the current cannot change instantaneously, right? But the voltage can. So because intuitively inductors are just wires, a very long wire, so the current it takes time to change its value. Okay, so we know that VL, so the voltage VL of T is L DIL of T over dt. Okay, this is L. So this is the basic equation relating the voltage of the inductor with its current. And capacitor is another device that can store energy. So this is a polar capacitor. If the capacitor is non-polar, then the symbol is like this. Can be plus minus or minus plus, but here we consider a polar capacitor because here we use DC voltage or DC current. So for DC current usually we consider a polar capacitor. So the longer lines here represent the negative, shorter one is the positive. Okay, again we have VC, the voltage across the capacitor, and the current is IC. Okay, in capacitor it is the voltage that cannot change instantaneously. Okay, so the current going through the capacitor is equal to capacitance C, which is farad. So units is farad, this is Henry. So IC of T is C, which is the capacitance, times dVc of T over dt. Again, we can see that the voltage cannot change instantaneously. All right. Now also, if you see these equations, you can see that, for example, the voltage across inductor only exists when the current is changing over time. Okay, so when the current is constant, then there is no voltage across inductor. The same with capacitor. So the current on capacitor is only flowing if the voltage across it is changing. If the voltage is static or it's on a steady state condition, then there's no current flowing through the capacitor. Okay, so those are the basics of inductor and capacitor. So let's solve a couple problems on first order circuit. First problem, we have this circuit plus minus 400 volt DC voltage with 100k ohm resistor connected to point A, sorry, this is point B, and another resistor connected to point C here. This is 50k, and I have a switch. This is switch. This switch connected to A, point A here, and there is a capacitor 0.1 microfarad. Let's call it plus minus V0. Okay, V0 is the voltage across the capacitor. Okay, so timeline. So we have a switch. The switch is moving to that direction, counterclockwise. But timeline number 1. Okay, timeline A. So A switch is moving from A to B at t equal to 0 second, and B, the switch, is moving from B to C at t equals 15 millisecond. And questions. Question A is derive the expression or expressions for V0 of t at all times. So meaning that V0 of t for t between 0 and 15 millisecond, and V0 of t where t is between 15 to the infinity time. Alright, so that's question A. Question B, plot the voltage, so V0 of t versus time. Okay, see, so time or times, maybe multiple time, when V0 of t is 200 volt. Okay, solutions. Solution for A. Okay, so you have two different timelines, right? So A, consider t between 0 and 15 millisecond. Okay, at t equals 0, when t is less than 0, we have the switch at position A, but when t is equal 0, the switch moves from A to B. So we have the switch is closing from A to B. So we have this circuit here for t between 0 and 15 millisecond. So let's draw the circuit. plus minus 400 volt, 100k ohm, and we have capacitor, not inductor, plus minus 0.1 microfarad. This is V0, right? And we need to find the expression of V0 here. Okay, so let's solve it. Okay, oh yeah, so I forgot to mention initial condition. So V0 is a 0 volt, so it means that the capacitor is not charged initially. Okay, so for t less than 0, the capacitor is not charged, it doesn't have any charge in it, so of course the voltage is 0. Okay, so we need that initial condition. So let's use KVL here, right? Since we know that the capacitor doesn't hold charge before, and we have a voltage source, so when we have this circuit, it means that this voltage source would charge the capacitor, right? So that's why we have the current on clockwise direction, because this voltage source is charging this capacitor. So, and the current here, since we only have one loop, then this current here is actually I0, or we can say it's IC, or the current flowing through the capacitor, right? Okay, using KVL, let's derive the equation. We have, say this is Vs, so minus 400 plus minus, right, plus minus 100. So let's say, okay, for simplicity, let's call it V0, Vs, Vr. Okay, so we have minus Vs plus Vr plus V0 equals 0. So that's coming from KVL, right? Okay, so we know that minus Vs plus Vr, but Vr is what? Vr is, let's say this is R1, so this is R1, let's call it R1, R2, and this is C, this is C. So we have minus Vs plus Vr. Vr is the current I0 times R1 plus V0, right? V0. Okay, but we know that I0 is what? I0, which is IC, is C d V over dt if the current is going in. Okay, so since the current is going in here, then we have minus Vs plus V0 equals to minus I0 R1, right? Vs plus V0 equals I0 is here C d V0 over dt, so V0 of t multiplied by R1. Okay, so we have minus Vs plus V0 equals minus R13 dv0 t over dt. Okay, so we can do algebraic manipulations. So you can multiply both sides with minus yeah, minus 1 over r1c, right, dt, and d v 0 over, okay, so we can remove the t for simplicity, over v0 minus vs, right? So that's what we have. Okay, so we can integrate this, since we start from 0 times 0, so from 0 to t minus 1 over r1c d tau equals integration from v0 at time 0 to v0 at time t, say dx over x minus vs. Okay, so we can work on these integrals. We have minus 1 over r1c t equals natural logarithm, so I will just call it log, so log of x minus vs should be absolute value, v0 t v0 0. Okay, and we can power it with exponential, so minus 1 over r1c t equals, so this is nothing but natural logarithm or log of v0 t minus vs v0 0 minus vs, right? So we have v0 t minus vs over v0 0 minus vs, and that gives us v0 t equals vs plus 0 of 0 minus vs times e to the minus 1 over r1c t. Okay, I hope so far is clear. Now, what is vs? We know that vs is 400 volts, v0 is 0, and we know that r1c is, sorry, 1, so we can plug in r1c to get 1 over r1c is actually 100, so that gives v0 of t is vs, which is 400 minus 400, so 400 is 1 minus e to the 100 t, and don't forget the unit is volt for t between 0 and 15 milliseconds. Okay, so this is the first expression. All right, second, for t between 15 or t greater than 15 millisecond, right? Because when t is 15 millisecond, the switch close from B to C, so it leaves us with this circuit 50k, let's call it R2. I have capacitor C plus minus V0, and this is per micro. Okay, now that the capacitor is charged, then when you have this circuit, it will uh, give the current or give the energy to be dissipated by this resistor, right? So let's say there is a node here, and we know that the voltage across the capacitor is the same as the voltage across the resistor, right? Because they are in parallel. So say this is the current given by this capacitor. So let's say IC, and this is the current flowing through the resistor IR. So by the KCL or Kirchhoff current law, we have IC must be equal to IR, right? But IC is minus C d V0 over dt equals IR is V0 R, right? Sorry, IR is V0 over R2. Okay, so we have d V0 over V0 equals minus 1 over R2C dt. So we can use the same trick, so you can integrate this from V0 T, I don't know, T1, V0 T 1 over X dx, integration for T1 to T minus R2C dt, where 1 over R2C is, you can substitute 50k and 0.1 micro to get 200. Okay, so why I have T1 here but I have 0 here? Because this defined for T from 0, but here is defined for T greater than or equal to 15 milliseconds, so that's why I put T1 there. Okay, and this is natural logarithm of x, absolute value v0 t v0 t1 equals minus r2c t minus t1. Okay, can we get v0 t1 equals e power minus 1 over r2c t minus t1, but we know that t1 is 15, right? So v0 t is v0 at t1 at 15, e to the power, this is 200, t minus t1 is 0.015 volt, right? So but what is v0 of t1 or v0 at 15 millisecond? So we can plug in t1 equals 0.015 to the previous equation here. Okay, and this is actually 3110.75 volts. Okay, so you can substitute t here with 0.015 and you will get 310.75. 0 of t for this time interval for t greater than or equal to 15 milliseconds is 310.75 e to the power minus 200 t minus 0.015 volts for t greater than or equal to 15 milliseconds. Okay, so we have the two equations. Okay, this one and that one. So those are the answers for A. What about B? B, we need to plot some graph, right? So let's do that. So we have, sorry, so we have V T, this is 5, 10, 15, 20, 25, and so on. And let's say this is bigger, 100, 200, 300, 400, 200, 300, 100, 0. This is the voltage. So on the y-axis is the voltage, on the x-axis is the time. So we have a critical time when t is 15. Okay, so when t is 0, what do we have? When t is 0, then e to the power of 0 is 1, so 1 minus 1 is 0, so v0 of 0 is 0. And we know that when t is equal to 15 milliseconds, the voltage is 310.75, so this 310.75 is maybe somewhere here along this line. This is 310.75 volts. So since we have exponential, so the plot will be like this, so it will rise exponentially. It will rise exponentially, and then here when it will decrease, right? Because when t is infinity, then e to the power minus infinity will go to 0, so it will decrease exponentially to 0. Sorry, so be red. So we will have this. Okay, maybe not that sharp. Okay, something like that. Okay, so this is the plot. C, what is C? C, we have time when the voltage is 200. Okay, so when the voltage is 200, so this is the voltage at 200, we have that there are two times actually. So here on the interval 0 and 15 milliseconds, so this will be millisecond, and it is voltage in volt, and this t in millisecond. And this one here, so when t is greater than 15 millisecond, we have another time where the voltage is also 200 volts. Okay, to find it, we can simply substitute. So first, consider the first equation here. Simply substitute for t0, t 15 millisecond, and this is for t greater than or equal to 15 millisecond. We have this equation, right? Let me copy it. Okay, so plug in 200 there, and we want to find the t, right? So 400, 1 minus e minus 100t, so 200 over 400, we have 0.5 equals 1 minus e to the power of minus 100t. So this is e to the power minus 100t is 0.5, or minus 100t is the natural logarithm, or log or 1/2, right? So So t is simply log 1/2 over minus 100. So t is, so log 1/2 is minus 0.6931 something. So t is 6.931 millisecond. Okay, so those are the steps. So let me indicate it with t1. Okay, so at t 6.9, actually we have the voltage is 200 volt. Okay, so for t greater than 15 millisecond, we can follow similar steps. So 200 is equal to 310. Sorry about that. So 310.75 e to the power minus 200 t minus 0.015. So you can follow similar steps and you will get, let me have t2. So t2 is 17.2 millisecond. Okay, so I hope you can follow how I obtain the solutions from this particular problem. If you have any question, send me email and come to my office hour. It's quite a long problem. We have another one. It is also quite long. So let me draw the circuit first. This time we have current source 15 amps connected to 10 ohm resistor. We have point A, point B, this is point B, and we have a switch. But the switch is connected to A. Five ohm. We have inductor. This inductor is 50 millihenry. Again, the voltage across this inductor is indicated by V0. It's V0 there. We have another switch, another point. So this is switch 1, switch 2 connected. This is point C. We have resistor 20 ohms. Quite complicated circuit. Well, don't worry. The timeline. So timeline A, switch number 1 at A for t less than 0 second. Switch 1 then moves from A to B at t exactly 0 second. C switch number 2 closest to point C for t between 10 millisecond and 20 millisecond. And D, switch number 2 opens at T exactly 20 millisecond. And here we only have one question, so what is V0 at T equals 25 millisecond? So the voltage across the inductor when T is 25 millisecond. Okay. Solution. Okay, so let's consider timeline A. So for T less than 0, what do we have? Initial condition. Yeah. Okay. So for a long time we have this condition, right? So the switch is at this position for quite a long time. So it means that this inductor is charged, right? When this inductor is charged, then what we have, there's no current there. I mean, there's no change in the current because the current is already at steady state. So di L over dt is 0. It means that the voltage across the inductor is 0. So what happens when you have inductor and the voltage is 0? It means that this inductor, it is just a short circuit, right? So you have this circuit 15 amps, 10 ohm, and you have 5 ohm, and the inductor is a short circuit, and you can say this is I0 at 0. Okay, so essentially I0 at 0 is just the current flowing through this 5 ohm resistor from this particular circuit, and we can use current divisor. Okay, so I0 at 0 is something multiplied by the source, which is 15. If you forget, then here's a simple intuition. You have two resistors, right, in parallel. It means that the currents flowing through this resistor will be different from the current flowing through this resistor. But since this resistor is 10 ohms and the other is 5 ohms, it tells us that the current flowing through this 5 ohm resistor has a greater value, right? Or there are more currents flowing through this 5 ohm than this 10 ohm, because guess what, 5 ohm has less resistance than 10 ohm. So it makes sense, right? Since 5 ohm has less resistance, then it implies that the current flowing through this 5 ohm is greater than 10 ohms. So the ratio should be 10 over the total, right? So you have 10 over 15 times 15 is 10 amps. Okay, so let me put in the box A0. Next we have T 0 T to what, to 10 millisecond. then the switch is closed. So once this inductor is fully charged, then the switch number 1 will moves from A to B. So we have this circuit 5 ohm, and this will be the inductor. Again, plus minus, this is 50 millihenry, plus minus we have V0. Okay, so let's call this VR then. VR, call this R. Okay, for now, just for this circuit, let's call it this 5 ohm resistor as R. This is L. Sorry, so use different colors. So this is R, this is L, and since this inductor is fully charged, then it will dissipate the current to this resistor, right? So this is I0, and we can use KVL. So what's our KVL here? We have minus, right? Minus V0 plus VR must be equal to 0. Okay, so minus, but what is V0? So let's go back here. We have VL is L DIL for dt, for current going into the inductor, but since the current is going out, then you have minus L di0 for dt. VR is I0 times R, right? So we can derive the equation. We have di0 over I0 equals minus R over L dt. Again, we integrate from 0 because we start from 0. Okay, so I0 0 to I0 t 1 over x dx, integration from 0 to t minus R over L d tau, and again this is what log, so log of x, absolute value of x, I0 t I0 0, and this is minus R over L t, right? This gives us I0 of t is e to the power minus R over L. We have I0 of 0 t. So R over L is it's 100. So I0 of t is I0 of 0 is 10 e to the power minus 100 t amps. Okay, don't forget the unit, amperes, and this equation holds for t between 0 and 10 millisecond. So don't forget. So we need to compute I0 at 10 millisecond, right? F10 e to the power of minus 100 times 0.01, so 10 times e power of minus 1, which is 10 over e. 10 over e is the constant 2.701828, and it comes out to be 3.68 amps. Okay, so this is what we have so far. Next, what is the next time step? Switch number 2 closes. Okay, so we have the following circuit. In the same circuit as this one, but we add another new resistor. So I add another resistor there. Let's call it R1, this R2, and the resistance is 20. So we have 20 ohms. So this is nothing but 5 parallel 20, right? So 5 parallel 20 is 5 times 20 over 5 plus 20. 5 times 20 is 100 over 5 plus 20 is 25. So 100 over 25 is 4. So we have 4 ohm resistor in parallel with this inductor. Okay, that's great. All right, so we can use the same steps to obtain the expression of the current here, but I leave that to you as an exercise, and simply you will get I0. So I0 here is I0 of t. So this is, oh yeah, I forgot to mention that this is for time between 10 millisecond and 20 millisecond. Okay, so I0 of t is between we have I0 at 20 millisecond, so 0.02 e to the power the new time constant, which is r over l, is, so r here is 4, l is 50 millihenry, so r over l is 80, so minus 80 t minus the time 0.01. So A0 of t is 3.6, sorry, this should be at 0.01 or 10 milliseconds, so 3.68 e to the power minus 80 t minus 0.01 ampere for t, 10 millisecond to 20 millisecond. So what is I0 at 20 milliseconds? So 3.68 e power minus 80, and 20 minus 10 is 10, so 0.01. So you can solve this, and I get 1.65 amps. Okay, we'll put that in red. Okay, last time, so when t is greater than 20, the switch number 2 is opened, and we are left with this circuit again. So let me copy it. Okay, so we have the same expression as this one here, where R over L is 100, right? But this is 0 of t is 3 point, sorry, 1.65 e to the power minus 100 t minus 0.02, right? 20 millisecond. So yes, that's the expression for the current amps. But the question is the voltage when t is 25 milliseconds. So remember that the voltage is VL or V0 of t is L I0 of t over dt, right? So L is 50 millihenry or 0.05. Di over dt is 1.65 minus 100 e to the power minus 100 t minus 0.02, and this turns out to be minus 8.26 e to the power minus 100 t minus 0.02, and this is the voltage for t greater than or equal to 20 milliseconds. But the question is the voltage when t is 25 milliseconds. So V0 at 0.025 is minus 8.26 e minus 100.025 minus 0.02 is 0.005, and you can compute this, and it is equal to minus 5.013 volt. Okay, so that is the final final answer. Okay, quite a long problem, but I showed you the steps, so if you follow my steps, then you don't have to remember the formulas. Just use KCL, KVL, and some calculus, differential equations, integration, then you will be able to solve this kind of problems without memorizing the formulas. Okay, so that's the end of this recitation class. If you have any question, please contact me. Thank you.